Hey, good people. Arthur Morris here. I hope all is well. In this video, we're going to look at related rates. So this still has to do with our derivatives, implicit differentiation. So let's take a look at a few of these application problems. So the first one, we have a ladder that's 25 feet long that's leaning against the wall of a house, and the base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So question A asks, how fast is the top of the ladder moving down the wall when its base is 7 feet, 15 feet, and 24 feet? So we'll look at the first two there. All right, so the first thing we want to do is to create an equation. And since we're looking at length and distance, we're going to use the Pythagorean theorem. So we have x squared plus, we'll call this up here y squared, and x squared plus y squared equals 25 squared, or x squared plus y squared equals 625. Okay. All right, so that's the equation that we're going to work with, and we're given the length of the ladder, and we're also given how fast the ladder is moving away from the wall with respect to the base. So we'll call that 2 feet per second. Dx dt is equal to 2. That rate of x with respect to time is equal to 2. All right, so let's see here. So we have the equation x squared plus y squared equals 625, and we're trying to find a rate, a speed, as how fast something is moving. So we need to find our first derivative with respect to time. Okay, so let's find our derivative with respect to time. D dt of each side. Okay, so derivative of x squared with respect to time, the variables are different, so I have to use the chain rule. So we have 2x, and then the derivative of x with respect to t is dx dt. Same thing with the y squared, 2y, and the derivative of y with respect to t is dy dt. And then the derivative of this constant is 0. All right, so our question asks, how fast is the top of the ladder moving down the wall? So we are trying to find, with that question, we want to find, let's write it up here. The question, we want to find dy dt. dy dt. How fast is this thing moving down the wall? dy, the change in y with respect to time. dy dt. So let's solve our equation for dy dt. So let's first of all, let's subtract the 2x dx dt from each side. All right, so negative 2x dx dt. And then let's divide both sides by 2y. So divide by 2y, divide by 2y, the 2's will cancel, so it leaves me with negative x over y times dx dt. So dy dt, let's see here, let's rewrite this up here, sorry about that. Left off my dy dt, which is what we're trying to solve for, so we definitely need that. All right, so dy dt equals negative x over y times dx dt, and that's a key equation we're going to come back to over and over and over again. So to solve or find dy dt, we need to know what x is equal to, what y is equal to, and what dx dt is equal to. Well, we know the value of dx dt is always 2. That was given. In this first case, it says when x equals 7, or the base equals 7, so we know x is equal to 7, but we also need to know the value of y. So we're going to use the Pythagorean theorem again to find the value of y. So x squared, or 7 squared, plus y squared equals 25 squared. All right, so y squared equals 625 minus 49. And then let's see here, So 576 y squared equals 576. And let's go ahead and take the square root of each side. So y equals the square root of 576. And we're looking at length. We know we would look at positive, negative, but we are looking at the length, so we're only looking at the positive aspect of this. So y equals 24. So when x is equal to 7, y is equal to 24. So now I have everything I need to plug into this formula. I know y is 24 when x is 7, and dx dt is always 2, as given for this problem. All right, so let's plug it in, and simplify. All right, so dy dt is equal to negative 7/12, and that was feet per second. Let's see here. Yep, feet per second. So negative 7/12 feet per second. All right, so when the base is 7 and the ladder is being pulled away from the wall at 2 feet per second, then the rate that the ladder is coming down the wall with respect to time is negative 7/12 feet per second. All righty. So the second part of the question said, well, okay, well, what about 15 feet? Well, it's the same thing. We have the equation that's super important to us for this problem for part A of what dy dt is equal to. And we know that dx dt is equal to 2, and then they're telling us, okay, well, what about 15 feet? Well, they're saying, well, let x equal 15 feet, and then tell me how fast the thing is coming down the wall. Let the ladder be 15 feet away from the base, and let's see how fast it's coming down the wall. So with that, we'll look at the 15 feet. We won't look at the 24 because, again, it's the same thing. So we know that dy dt from what we solved is negative x over y times dx dt. So that's the equation that we found. That's what we saw for dy dt up above. So this time x is equal to 15, so we have to go through the same process of finding the value of y, because we need x, y, and dx dt to find dy dt. So using the Pythagorean theorem, have y squared equals 25 squared, and let's go ahead and take the square root while we're doing all of this. 625, 25 squared, 625 minus 225. So y equals the square root of 400, which is 20. All right, so when x is 15, then y is 20. Okay, and then from there we just plug everything in again and simplify. Dy dt is equal to negative 15 over 20 times 2. Well, we know negative 15 over 20 can be simplified, or let's just go ahead and multiply. It may be a little bit easier to see. Negative 30 over 20, if we multiply 15 times 2 and then simplify that to negative 3 over 2. All right, so that's how fast the ladder is moving down the wall. If the ladder is 15 feet, the base of the ladder is 15 feet or 15 feet away from the base of the wall and being pulled away at 2 feet per second. Okay, so you would do the same thing for x 24 feet away, plug it in the same way. All right, let's look at part B of this problem. It says, consider the triangle formed by the side of the house and the ladder and the ground. Find the rate at which the area of the triangle is changing. So we're looking at area this time, and when the base of the ladder is 7 feet away from the wall. So we're going to use that information of what we found at the first of this problem, where we said if x equals 7, then we use the Pythagorean theorem to find that y is 24. and then we solve for dy dt to find that that is negative 712. So we're going to use that information. We're not going to solve all of that again, but now we want to find the rate at which the area of the triangle is changing. So we need to find the derivative with respect to time of both sides. And remember, we have that constant multiple of 1/2, so it'll just stay outside. On the right hand side, we'll have to find our derivative of x times y. Okay. Now on the left side, the derivative of a, the variables are different with respect to t, is simply dA dt. Cool. Done there. On the right hand side, we have to use our product rule. So we have to find the first times the derivative of the second plus the second times the derivative of the first. All right, so x, the first, times the derivative of y with respect to dt, so dy dt, plus the second y times the derivative of x with respect to t, so dx dt. All right, so the rate of change for the area with respect to time is 1/2 times x times dy dt plus y dx dt. So now all we need to do is substitute and simplify. All right, all right, all right. So let's see what we have. All right, so x is equal to 7. Let's use some brackets here since we're going to multiply. Dy dt in this case is negative 7/12. Again, that came from the previous work that we did for this problem. And then y is equal to 24. And dx dt is equal to 2. All right, let's calculate. So let's see here, dA dt, 1/2, negative 49/12 plus 48. And I'm sure you could throw this in your calculator at this point, but let's go ahead and go through it. Let's get a common denominator of 12. So the 48 will become 576/12. And then let's combine that to 527/12. And then let's multiply. Let's multiply by 1/2. So 527 all over 24. All right, all right, all right. And that's how you would find that area. And since we're looking at area, that would be square units, so feet square per second. Okay. Well, what if we're asked to find the rate of which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet away from the wall? So now we're looking at a little bit of trig here, and I'm going to use cosine. Cosine of theta equals adjacent over the hypotenuse. Adjacent over hypotenuse. Those are two things that are not changing. It's the wall uh, and hypotenuse. Okay, so let's see here. All right, so let's go ahead and find our derivative of this with respect to time. Adjacent would be y over 25. Okay. Let's go ahead and rewrite that y over 25 to 1 over 25 times y, so we can keep that constant multiple out there. All right, so the derivative of cosine theta, which is a different variable with respect to time, means that we need to use the chain rule. So our derivative of the cosine theta would be negative sine theta, and then derivative of theta with respect to time would be d theta dt. And then over here on the right hand side, derivative of y with respect to time would simply be dy dt. All right, so we want to find the change of the angle, so that would be d theta dt. So let's solve this equation for d theta dt by dividing both sides by negative sine theta. So d theta dt, and let's divide by negative sine theta. That means that would go in my denominator. So sine theta, let's see here, 25 sine theta times dy dt. So we have d theta dt is equal to negative 1 over 25 sine theta times dy dt. So looks like we need two things. We need dy dt and we need sine of theta. So we've already found dy dt from the previous problems that we looked at. When the base was 7, we found that dy dt was equal to negative 7/12. So we need sine of theta, and sine is opposite over hypotenuse. So sine of theta equals opposite over hypotenuse. So the opposite of this angle is 7. The hypotenuse is 25. So sine of theta equals 7 over 25. So we have everything we need now. We have sine of theta. The value of that is 7 over 25. And then dy dt, the value of that is negative 7/12. So let's take it back over here and plug it in. So d theta dt is equal to negative 1 over 25 sine of theta. We said the value of that is 7/25 times dy dt, which is negative 7/12. So now I'll just throw this in parentheses over here. All right. So let's finish this off. Let's see, the 25s cancel. That leaves me with, I'm running out of room here, leaves me with negative 1/7 times negative 7/12. So negative times negative makes positive, and the 7's cancel slightly. So now I have 1/12. So changing that is 1/12 radians per second. 1/12 radians per second. All right, all right, all right. So again, we use trig to help us find the rate of change for that angle. All right, and the last example that we're going to look at is when an airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles away, the radar detects that the distance s is changing at a rate of 240 miles per hour. What is the speed of the plane? So the speed of the plane would be dx dt. We're looking at x here, how fast this plane is going. So the speed of that plane would be dx dt. So we'll use the Pythagorean theorem again, having x squared plus 5 squared equals s squared from the given diagram here. And let's find the derivative with respect to time of this equation. So let's see here. And my 5s will never work out. And let's try one more time. Okay, whatever. All right, so equals s squared, then d over dt. All right, so let's find the derivative of both sides. So the derivative of x squared, have to use the chain rule with respect to time, the implicit differentiation. So 2x, derivative of x is dx dt. Derivative of 5 squared, derivative of any number is 0. And then our derivative of s squared with respect to time, 2s times ds dt. And we need to solve this thing for dx dt, so let's divide both sides by 2x. So the 2's will cancel, so that leaves me with s over x times ds dt. All right, so to find dx dt at any given time, we need the value of s, we need the value of x, and we need the value of ds dt. All right, so we have ds dt that was given to us. It says that the distance of s is changing at a rate of 240 miles per hour. So that's ds dt when s equals 10. But we also need the value of x. So when the altitude is 5 and s is equal to 10, what's the value of x? Well, again, that's the Pythagorean theorem. So that's 10 squared, or x equals, and I'm going to go ahead and I'll rearrange and modify the Pythagorean theorem. You can go all the way through it if necessary. 10 squared would be 100 minus 25 squared, 5 squared would be 25. So x equals the square root of 75. We could break that down. Why? Because we know that 25 times 3 equals 75. And we know the square root of 25 is equal to 5. All right, so in this scenario, x is equal to 5 times the square root of 3. All right, so let's come back over here and substitute everything in. When s is 10, x is equal to 5 times the square root of 3 times 240 ds dt. All right. Let's see here. So we know that 5 will go into 10 2 times. And 2 times 240 is 480. And if it asks for your answer in decimal form, then you can find your decimal form from there. 480 divided by the square root of 3. However, if it asks for exact form, we need to rationalize our denominator and simplify. So 480 times the square root of 3. The square root of 3 times the square root of 3 is simply 3. And 3 would go into 480 160 times. Which is approximately 277.13 miles per hour. Alrighty, good people. These problems do take some practice. Make sure you look at the examples that you have in the textbook, or examples with the problems that come up. I hope you found this video to be helpful, and I will see you on the next one. Thank you.